hear me. Nice to be here. It's sad circumstances. The paper maybe come to Paulo quite late last night, so I didn't have time to check my lecture. But it's okay, I think. So Antonio has asked me to talk a little about, in general, about what is quantum chemistry, what can quantum chemistry do. And this is what I'm going to do in a rather light way, I must say. So if somebody feels that I'm too light, I'm sorry. Experts in the field will think that it is a little bit too light, but I understood that we were not all experts in quantum chemistry here, and that it might be interesting for you to hear a little bit about what quantum chemistry is about and what it can do. I'm sorry I don't speak your language, but you will have to bear with my English, I'm afraid. Now, what is quantum chemistry? Well, I mean, there are two primary ways to view the area of quantum chemistry. And the first and the most important of these two areas, I still think, is that it is a tool to understand the chemical bonds and what electrons are really doing in the molecule. Now, when I talk about this, I mean it is a tool for the qualitative understanding. Now, it didn't take long after the Schrödinger equation that people started to try to use this for molecules and understand, in using the language of quantum mechanics, what the chemical bond was. And we all learn about this today in the textbooks. It's all over the textbooks in chemistry. Hybridization of the carbon atom, the ligand field in transition metal complexes, all these fantastically powerful qualitative methods which have taught us what the chemical bond is all about. And most of this was developed in the 30s, as a matter of fact. A few things came a little bit later, but most of it was already developed in the 30s. So quantum chemistry has given us the qualitative understanding of the chemical bond and what what electrons are doing in molecules. But then there is a second step, a science that uses modeling to understand chemistry both qualitatively and quantitatively. And that's what we call computational quantum chemistry. And the goal is here a little bit different. The goal is now to solve the Schrödinger equation. Up here, we use the concept of the Schrödinger equations and very simple models to understand what is going on. But now, if we want to have quantitative results, then we need something else than just a qualitative picture. And as I said, it all dates back to the formulation of the quantum mechanics in the middle of the 20s. And in principle, if one knows the solution to the Schrödinger equation, we can compute all properties of the quantum mechanical system. Now, of course, if you have a heavy atom, as I talked about in Karambu, you have to replace the Schrödinger equation by the Dirac equation, but this we don't worry about. And the first attempt to do this was actually already done by Heitler in London, as most of you know, on the hydrogen molecule in 1929. So quantum chemistry quickly was, and this is what you might call the start of quantum chemistry. The application of quantum mechanics on molecular systems. And it was a rather pessimistic view in the beginning of this, and this is a statement that most of you probably have seen already by Dirac from 1929, that the theories are known, but we cannot apply them because they are so complicated. Or in simple terms, the Schrödinger equation cannot be solved. Too complicated. And that's, of course, was one of the driving forces for all the simplifications in quantum chemistry, all the simple models that were developed in the 30s and the 40s and also in the 50s and 60s, as a matter of fact, like Paris-Apart Popel's approach in pi electron system, like the C and the O method to describe Hückel, etc. All these semi-qualitative or semi-empirical methods. Yes, I will not say much more about this. These are the early days, as I already talked about. The nature of the chemical bond, ligand field theory, Hückel theory, central field model for atoms. Actually, the first computational effort in quantum chemistry was probably the one done on, unless you may not call that quantum chemistry because it was done on atoms. But this was a very important starting point, trying to solve to find the orbitals in atoms, other than hydrogen atom, of course, which was known from the Schrödinger equation exactly. And they developed in England, Hartley, and also, of course, Hawkins later in Russia and in the United States. But the calculations were essentially done in England. They developed something they call a central field model, in which you averaged out the interaction between the electrons and just treated one electron at a time. And this is the starting of the most well-known and most fundamental of the quantum chemical methods, namely the Hartree-Fock method. So this was already developed in the early 30s. Another very, very important concept, qualitative concept in chemistry is, of course, the Born-Oppenheimer approximation, which allows us to define a molecule. Because it splits up, and there was a lecture on this in Kathmandu, for those of you who were there. It divides up the motion of the electrons and the motions of the nuclei. So the energy of the system is described, for the electrons, is described as a function of the coordinates of the nuclei. And then the motion of the nuclei are solved with this as a potential. And this energy surface is, of course, the key to our understanding of what the molecule is, because it has a minima in which we can define the geometry of the molecule. It has barriers between different minima, which we can define as an energy barrier, a transition state for a chemical reaction. So it gives us the language to talk about molecules. This is one of the most fundamental approximations. It is an approximation, of course. And this was also discussed in this lecture in Kathmandu. But it's a very, very good approximation. There are exceptions, and the most important exception when you need to do something beyond this approximation is that when you have several energy surfaces crossing each other or very close in energy. Then you have non-Born-Oppenheimer effects, and one of the more important of these effects that at least inorganic chemists have heard about is the Jahn-Teller effect. So there are exceptions, but in almost all cases, this is a very valid approximation. And even if it is not valid, it's the starting point. One should remember this, that this is always the starting point. If you want to go further, you can allow these different energy surfaces to interact, but you always start with calculating them. The Dirac statement that we cannot solve the Schrödinger equations was all the time challenged. Because we really, scientists, especially the quantum chemists, really wanted to try to solve the Schrödinger equation. And when, after the Second World War, the computers started to develop, one saw a new possibility. Maybe, if we cannot do it by hand, which was the way Hartree had done it for atoms, and actually my own professor, Professor Inga Fischer-Hjalmar, in Stockholm, did a calculation on the ozone molecule on one of these machines. Professor Lundin in Uppsala was known for having a computer in the top floor of his department. That computer consisted of students, which he hired for a cheap amount of money to sit and do this. And that's what the way he produced his doctoral thesis, Professor Lundin. So people really wanted this, right? And now comes an electronic machine that can do this for you. And immediately people knew how to do it. I mean, we already since the 30s, we had methods, those Hartree-Fock especially, and that was the first one tried. And there were essentially two programs in the beginning, the so-called informal program and polyatom by Clementi and his group, at first in Chicago and later at IBM. And then in Harrison, Chismadia, Sutcliffe, and others with the polyatom program. And they were developed in the early 60s. The Gaussian code came a little bit later. Mr. Popel, who has become Mr. Quantum Chemistry in a sort of way, didn't like this in the 60s. He didn't think it was fast enough. He said, okay, you can do it, but it takes a long time. And I know myself that it took a long time, because when I started my scientific career using this program here, we were doing molecules like ammonia, Hartree-Fock calculations, and it took a very long time. They once called us up from the computer center in Stockholm, actually our professor, we were very young, and said, there's something wrong because this calculation never stops. And it was just an SCF calculation. That took a long time. So Popel was against it, and he said, I will use C and the O. But a little bit later, he changed his mind, and in 1970, we got the first version of the Gaussian. Computers were very primitive. Now, this is an extremely primitive computer. That's the computer called BEST, which was available in Stockholm in the early 60s, 1960. And it had a memory size, which in hexadecimal counting was FFF. That was the number of locations. Had to be programmed in machine language, etc. So things started out primitive. But, you know, today, that's a completely different situation. It went very quickly, and today we have computers which can do almost whatever we like them to do. And tomorrow we will have even more. Development is not stopped at all. I do most of my calculations myself on this computer here, which has 1 gigabyte of memory, 80 gigabytes of disk, and a 3 gigahertz processor, and it's not working very well, as a matter of fact. But it's what you need for many things. So we are in a sort of dream world compared to what we had in 1960. One couldn't dream of this development. So it's possible to develop, and at the same time, of course, since 1960, we have passed through a development of the methodology which goes with the computer. When I started myself in the middle of the 60s, or about there, computers were considered as being something dirty. And you hired special people. If you really need to do some calculation, you hired special people to do the programming for you. So you didn't have to wet your hands with that stupid thing of writing programs. And then you gave them a task and they came back to you with the result. And I had a professor in the early days of my education, which you may know the name of, because he's a rather famous professor, Professor Oscar Klein, in theoretical physics in Stockholm, Klein of the Klein-Gordon equation. And he hated computers. Actually, the students were not allowed to use them. If you couldn't think with your mind, science was beautiful. It was beautiful geometrical shapes and things. It was not numbers. Numbers is destroying science. So we had to hide the little group who wanted to do calculations and use this early computers. We had to hide that. But when I really started, I understood that for a quantum chemist, the computer and the science goes together. The development of the quantum chemical methods that took place in the 70s and 80s and 90s were very, very much entangled with the development of the computer methodology. For example, one little thing that changed things very much for us was the invention of the disk. When you do calculations, and I will talk a little bit about that, you need to store and resort and transform very large amounts of numbers. And to do that with a tape was very, very difficult, because you can only read the tape sequentially and write it sequentially, one number after the other. With the disk, you can suddenly sort things. You can put them here and there and everywhere. And new technologies, new algorithms were developed because of this technology development. So there was a very, very tight entanglement between the computer and the science. And those who understood that had an advantage. Those who did not understand it lost in the game in the 70s. And we had two schools in Sweden in these days. One which was very much computerized and was called programmers, and another which was a high level of scientists and didn't really like computers. And I will not go into any detail of that. Let's look at some example, Hartree-Fock theory, and now if you don't like equations, I promise you it won't be much. But I want to give you some numbers so you get a feeling for what we're dealing with here. In Hartree-Fock, you want to determine some coefficients, the coefficients of the molecular orbitals, by solving an eigenvalue equation that looks like this, where this is the so-called Fock or Hartree-Fock operator, which has matrix elements that look like this, and this describes the one electron part of the Hamiltonian, the kinetic energy, and the interaction of the electron with the nuclei. And this describes the interaction between the electrons in the so-called mean field approximation of Hartree-Fock. And as you can see, these are four index quantities. And this is the whole problem of Hartree-Fock, to handle these numbers. The basis here, which you solve this equation, is a basis of atomic orbitals. So on every atom you put the number of functions, say 10, 20, on every atom. Now if you have 100 atoms and 20 functions on each, you have 2,000 of these functions. So that's approximately the size of the problem. So Hartree-Fock technology is the art of computing, storing, and retrieving integrals with four indices. Actually, this is true also for later technologies like configuration, interaction, couple cluster, etc. But this is the first place where it occurs. Now, if you have 100 of these functions, the number of terms here becomes, because of symmetry, you can divide by 8, 1.25 times 10 to the 11, which is 10 to the 12 bytes. You see the problem here. If you want to store and handle all these numbers, you really cannot do it. Not even today. That's a terabyte of information. Maybe you could do it today, but then you go to 2000 and then you cannot do it again, because this is an N4 increase. So the question is, can you really do this? Can you make this method such that you can do a big molecule, a molecule which the chemist might be interested in doing? The answer is that when we started in the 60s, you could not. N was limited to less than 100 functions, and you got small molecules. Today, on the other hand, you can. Because today the computers have become faster, storage have become bigger, etc., etc. But we have also developed, and this is even more important, new and more efficient technologies to deal with this. And one way to deal with these integrals, these numbers, is not to deal with them at all. Because if you have to calculate them, and then you put them somewhere and then use them. But one modern technology is to calculate them and use them and then forget about them. But then you need them again. Or then you calculate them again. It's fast. CPU time is fast. So you calculate them when you need them. And then it turns out that you don't have to calculate more than approximately 10% of them, because you don't need more than that. And you need less and less as the calculation goes on. For larger molecule also, the number of integrals you need actually doesn't grow as N4, but it grows as N2. And methods have been devised that grow linearly with the number of N. So that you can really do, when your molecule becomes twice as large, the problem becomes twice as large, not 16 times as large. So all these development, and you can use parallel computers. The development of the computer technology also puts the poor quantum chemistry in new situations all the time. First, we had these primitive scalar computers, and when you learned how to deal with them, somebody invented something called vector machines in the 70s, And then you have to we make new types of algorithms which could effectively use those. And then in the 80s came parallelization. And you had to program for parallel machines. And nowadays we have clusters of PCs, a few hundred of them, and we want to run on all of them. So with this development, we can now do calculations at the Hartree-Fock level for quite large molecule, and this molecule here is not too large, as a matter of fact. Calculations have been done on molecules of almost this size, and tomorrow we'll see it. And we can actually foresee a future when we can replace molecular dynamics as a method to improve on X-ray structures with quantum chemical calculations. And molecular dynamics is a very shaky methodology. So I think that tomorrow people are going to deal with this type of problem, maybe somewhat reduced, but that is more for practical reasons. Actually, I think we have now reached the limit, which is practical, in the sense that we don't need to do bigger molecules, because it's not practical really to do a quantum chemical calculation on a protein of 1 million Dalton or something. Really not needed. Nobody's interested in that type of information. But you need to do it on a fraction, quite sizable fraction of it, to study an active site, to study the conformation in a specific part, then you can do that. So we actually have reached the limit. But there is another problem. This method, Hartree-Fock, is that good enough? It's an approximate method, and we know the limitations of this method very well by now. We know it's reasonable for geometries and first-order properties for normal molecules in their ground state close to equilibrium. But this is not enough. We need to be able to compute energies, for example, dissociation energies, barrier for the chemical reaction, etc. And Hartree-Fock theory cannot do this except for some trivial cases. And this is called, the error here is called electron correlation, and I will not talk about that in detail, but I will see how can you go beyond the Hartree-Fock approximation. Well, then you have a whole variety of different methods which you can use, but they become more and more and more complicated. Already in the 20s, this problem was tackled by Roos on the helium atom. I saw a quite interesting poster in Kasambu on the helium atom, by the way, using Bohr-Sommerfeld theory. Quite interesting. The Hartley-London, if somebody were here who did that poster, I'd like to have a chat with him. Actually, the Hartley-London wave function is not Hartree-Fock. It's something which later became known as valence bond theory, which many chemists know about. And it gives a better binding energy than Hartree-Fock theory for the hydrogen molecule. Something else which is called configuration interaction was already described in 1934 by Frenkel, and is something which is used extensively today. But the most important thing was actually something that became apparent to the quantum chemists in 1991. There was a conference in Menton in 1991 where a Canadian scientist by the name of Axel Becker presented a series of results for 55 test molecules, which actually had been used earlier by Paulo to test Gaussian, with a new so-called density theory method, density functional theory method, and proved that he got very good accuracy for the binding energies in all these molecules. I remember a dinner after that conference, we were all sitting around the table, and John Popel, who still didn't like this, said that I'm going to kill this theory, and there must be something wrong with this. So he decided that he was going to program it and have it programmed, or program it himself, I don't know. He actually did most of his programming himself, and put it into Gaussian, so he could work with it and prove that it was wrong. That's what he said explicitly. And more quantum chemists know what came out of this. An explosion in quantum chemistry came out of this. And this all goes back to a guy called Kohn from 1964, who had suggested an alternative to Hartree-Fock, which he called density functional theory, where he showed that the energy of a quantum mechanical system can be described if you know the density. A wave function is a very complicated function of all the variables of the electrons and so on. The density is a function of 3 variables. And for a long time, this was not believed to be useful at all in molecules because of the approximate nature of it. Because even if you could prove the existence of such a functional of the energy, you couldn't find it. And the attempts to find it were futile in the 60s and 70s. It was this key contribution in 91 that, so to say, opened the eyes of the quantum chemists. And it started to be used on a large scale. And I think Professor Popel should be very happy for Mr. Kohn, because that also opened the eyes of many members of a certain committee in Sweden who were chemists and did not think that quantum chemistry was very useful until they suddenly saw a lot of applications emerging in biochemistry, for example. Yeah. I don't think I need to talk about molecular orbitals, so let me jump this. I don't have time for this. This is a lot of technology, which I will not talk about. Let me say something about density functional theory, because it has become so important. These equations are very similar to Hartree-Fock theory. It is actually Hartree-Fock theory, those equations I showed you before, with an added term to describe electron correlation. The thing that Hartree-Fock could not describe. So actually some think about density functional theory as Hartree-Fock theory corrected for so-called dynamic electron correlation. And computationally it means that density functional theory is the same as Hartree-Fock theory. The same effort is needed as we have to use in Hartree-Fock. And I already told you what you can do with Hartree-Fock theory. So now it turns out you can do the same thing with density functional theory. But there is a problem, of course, as always. And those who were in Kasambu and heard me talk there know that I did not talk about density functional theory at all. I talked about other methods. And this is not the solution to the quantum chemical problem in general, but it's a very good approximation in many circumstances. And it has certainly brought quantum chemistry to the general chemists and the biochemists. And yeah, let me skip that also. Well, maybe I should say something about the development of these methods, because a lot of people have worked with that, developed different methods. So I told you that before 1970 we had Hartree-Fock theory and essentially 2 programs, and Popel was against it, but Popel did something. He was a curious man. So in the late 60s, he always said that ab initio quantum chemistry, Hartree-Fock theory, is about 100 times slower than CNDO. This is not good enough. This is not going to be useful. If we could bring it down to at least a factor of 10, then it might become useful. But he couldn't help thinking about it. So I think it was in 1968, he had an idea how you could make the calculation of all these 4 index quantities, the integral, much faster. And thus, he went to Florida and he wrote the program, which later became, in 1970, the first version of Gaussian. And then he transformed, because he showed now it was 10 times faster. So this is his early key contribution, is to make the integral calculation so much faster than it was before. There were other people working with similar methods. Actually, one of my students was doing that in the late 60s. We developed a program called Molecule, which also had the same features as Gaussian, being much faster than the older programs. Then came different methods of dealing with the electron correlation problem, and also problems dealing with others than normal molecules in their ground state, excited states, chemical reactions, etc., for which you have to go beyond Hartree-Fock. Couple cluster theory, which I will not mention the name of, is probably the most accurate of all quantum chemical theories today. It's very computer intensive, but it can be made very accurate. This is some ideas of how the development is going to develop. And actually, this is 2001, and we are already quite a way on this road. For example, this is a thing we are working with ourselves, combining density function theory and other more classical methods to take away some of the shortcomings of density functional theory. Large-scale applications, of course, that's only a matter of improving computer efficiency. And now one also have to combine in maybe a more advanced way. This is already done, of course, combining quantum chemistry with classical methods to treat macroscopic or mesoscopic systems, like solutions, proteins, etc. But there's a lot to be done here. I saw in Caxambu, in Brazil, there's much done on molecular dynamics simulation, Monte Carlo calculations, and so on. But I would like to warn you a little bit about all these applications, because our force fields are still very primitive. They are actually lacking a lot of information, and people who critically analyze some of these results see that there are quite large effects which still are missing. There's still a lot of work to be done here, anyway. And there are, so to say, areas of chemistry where we are starting to do things like photochemistry involving excited states, where some quite interesting results are coming out today, but there's lots more to do. And Dan is going to talk to you about properties, I guess nonlinear properties and things like that in optics, which is quite things we can calculate. There's a lot of properties that one can calculate that today, which actually are very useful for chemists, like NMR shielding constants, etc. So if one looks at the applications, how much time do I have, by the way? 15, 20 minutes. Okay, fine, good. This is just some typical examples of calculations that are being done today. Intermolecular forces, and that is especially for generating force fields for MD, and for studying small clusters, etc., weakly bound systems like water clusters, droplets, etc. Electron spectroscopy, this is an electronic spectrum of still beam molecule. Photochemistry, and this is a picture I borrowed from Mike Robb in London, who is doing a lot of photochemistry studying on organic molecules, how the reaction goes and where the conical intersections are that drive the reaction, etc. There is a so-called funnel here, for example, on this surface. Molecular structure, and this is actually one example which I will spend some time on. Vibrational spectroscopy, and I said electronic properties, etc., etc. Actually, all fields of chemistry can be influenced by theory today, from analytical chemistry to medicinal chemistry and pharmacological chemistry. I know we did some calculations on the adhesion forces in the chromatograph once, which used by an analytical chemist to be able to separate different aromatic systems. So you can use it there. You can use it, of course, in biochemistry. It's a very large application area today. I have a friend in Stockholm, Professor Per Sigban, who's done very, very important work on enzymatic catalysis, trying to understand the mechanism of the reactions that take place in cytochrome C and photosystem 2, etc., etc. Very successfully. So it's very, very powerful approach to understand. So, and this is enzymatic catalysis, and actually This is something I'm going to talk about a little bit as an example. This is some work we did about 5 years ago, just by chance, as a matter of fact. And it turned out that we were able to kill one of the hypotheses in biochemistry, rather fundamental one, as a matter of fact. And this is, of course, always nice when you can do a thing like that. Biochemistry, I don't know if there's any biochemists in the room here, but of course, then they can come and hit me afterwards. They are full of speculations. They have all these pieces of knowledge on very complicated systems, and then they put them together and look at them, and then they try to figure out some system around that. And the base is often quite weak. And this is one of these speculations which turned out to be wrong. This is plastocyanine, which is a blue copper protein. There are a number of those. They act as charge transfer carriers, for example, in photosystem 2. They transfer electrons from the active site and to the active site. So they are electron transfer proteins. They are blue, they have a high reduction potential, they have a very distinct EPR spectrum. And all these properties made the biochemists think that there's something special about this. This doesn't fit with a normal copper 2 ion, 4 coordinated. And actually the copper atom is strongly bound to a cysteine residue, and this is a key feature here. The function is that it's an electron transfer protein, as I already said. But it has a very strange structure. It is trigonal, both in the copper 1 reduced and in the oxidized form. Now, everybody who's read in organic chemistry knows that copper 2 has a tetragonal structure, because there is an empty d orbital, that's D9. There's an empty d orbital which has 4 fingers pointing out. I cannot do it with my hand. And there's a blackboard. But anyway, and there's a hole there. There's only 1 electron in that d orbital. So the ligands want to point in there with their electron pairs. And that makes a tetragonal structure. And other structures are quite unusual. But this is actually a quasi-trigonal structure with 1 or 2 very distal axial ligands. So it's intermediate between the tetrahedral copper 1, because copper 1 is a closed shell, it's a tetrahedral structure, and the tetragonal copper 2. Now, of course, from the point of view of charge transfer, this is excellent, because it means that there is not much reorganization energy. Charge transfer is always hindered by the fact that when you take the electron away, you put the electron that is around and will reorganize. And if you've read something about Marcus theory, there is an equation that shows how this is done. This reorganization energy is a major term in this to determine the speed of the electron transfer. If it is small, the speed will be larger, of course. So here we have an intermediate structure, and you don't have to look at all this here. So people were thinking, why is it that nature has created this structure which is so perfect for electron transfer and so unnatural for copper 2? Well, there were 2 theories. Actually, they are the same, more or less. One Swedish theory by Professor Malmström from Gothenburg, and one by Professor Williams from Oxford. The Swedish one was called the induced rack theory, and the English one the entactic state theory. And they both say that the protein creates a preformed rigid chelating site with a geometry which is in conflict with that preferred by the metals. But as you can, if you remember the protein, it consists of, it's rather firm, it's rather solid protein with only beta sheets. It's not very flexible. So you could really think that. So in spite of the fact that the metal would prefer another geometry, it cannot, because of this rack, which is constructed by the construction of the protein. And then you put the copper up there in a predetermined site. Nothing you can do. And this theory was actually primarily a theory of a metalloenzyme that later became some sort of universal principle for structural functional relationships in biochemistry, and was actually extended to a sort of general theory which was used in many contexts. Now we wanted to calculate the spectrum of this protein, electronic spectrum. And as I said in Kashamboom, the first thing you do when you do a quantum chemical calculation is to calculate the structure of your system, because you cannot trust X-ray crystallography, especially not in biochemistry. Errors are very large. But you can trust your calculation. That one is good. Today we know that we can calculate geometries with very high precision, higher than most experimentalists can. So it's exception, small molecules, microwave spectroscopy, etc. But for larger molecules, this is true. So we also, of course, if you do a quantum mechanical calculation on a protein, you have to select out the piece that you can handle. So you have to take out the active site and replace the rest of the protein by some charge field or some model potential or something, and you have to model your ligands. So this is the model of the active site. It has two imidazole ligands. Of course, they are models of histidine. And there is this one here, which is a model of cysteine, and then there is another ligand, which is on a larger distance, which is a model of methionine. This was then done with density functional theory, but density functional theory is a little bit shaky for metals. So it was tested with a more accurate method for the metal ligand distances. And I won't go into the details. Okay, now you may not be able to see this very clearly, but remember now that the rest of the protein is gone. Not there. So there's no strain in our model. There's no rack there that can hold these stiff. So you expect, of course, that, and actually thinking about the rest effect, I don't understand why we did it. Because since we know that copper would become tetragonal, it would go away from the protein environment. And that was a little bit strange to try to optimize the geometry then. But it turned out that it didn't. It stayed at the biochemical structure without the protein, without the rack. It still stayed there. And this you can maybe not see very clearly here, but the copper is in the middle here, and then the green thing is the experimental structure, and the blue and white and yellow, etc., is the theoretical structure. And they are actually on top of each other, with some exceptions which have to do with the rotation of these ligands and so on, which obviously are affected by the rest of the protein. But when it comes to the site and the coordination of copper, this is exactly as in experiment, without the rack. And we were, of course, very surprised. Here are the numbers, if you want them. And it's especially these angles here, which one should look at. You see? They are perfect. There are many variants, experimental variants of these proteins, and then you can get the variations in the structures. And here you can see the difference between DFT and more advanced theories in calculating metal ligand distances. Especially this bond here. And this bond here turned out to be very crucial. For the question you immediately ask yourself, why is it like this? Now you have to understand it. And then you start to look at your wave function, and looking at wave function can tell you a lot of things. It turns out that this negative sulfur in the cysteine ligand, which is an S minus, it has two lone pairs. One sigma pointing out, and one pi, which goes like this. Maybe if there's a chalk, I could draw it. Yes? I don't think I have a picture of it. And then there's a sigma lone pair, which is mainly 3s. And here is copper. And it turns out that the sulfur binds to copper with the pi lone pair, not the sigma. That bond is stronger. So what happens? Here is the half-empty d orbital, and here you have overlap. And here is the other ligand, nitrogen, nitrogen. So you get 3 ligands, but 4 holes. It is quasi-tetragonal, but there are 3 ligands. This is a rather delicate balance between sigma and pi bonding to the metal, and in some of the variants of this protein, which I'll show you later, it is switched to the other, and then the structure changes to more tetragonal. So the theoretical structure is virtually identical to the experimental one in the blue proteins. Actually, we calculate that the CO1 geometry is slightly strained, but the CO2 is not. And the corresponding tetragonal structure is more than 20 kilojoules per mole less stable. The known strain is needed to create a trigonal structure. The conclusion is that kappa 2 prefers a trigonal structure with this ligand, cysteine, and that's the key ligand. Methionine and 2 histidines. Nature minimizes the reorganization energy by the choice of ligands, not by strain. The strain does not exist here. The entactic state theory is not correct. It's much simpler than that, but it's quantum mechanical. It's not structural, it's quantum mechanical. Well, that's also in a way structural, but in a more complicated way. So you could never figure this out without knowledge about quantum chemistry and the chemical bond and wave functions and so on. That would never give you this answer. Just looking at the structures. Now then you can also, of course, do what you primarily wanted to do. You can calculate the spectrum of plastithionine. And that was done, and we turned out that with the structure we had optimized, we get a fine agreement with experiment, and actually you can see that there's quite some effect here of the protein surrounding it, which is included in the second calculation here. This you cannot do with DFT. And you have to use more advanced methods. So the blue color of this protein could be calculated. Now this work has actually been extended to a large number of proteins by now of similar character. And the conclusion of this study in general is that the cupric geometry is not strained, as I said. The structure is determined by the kappa cysteine bond, distorted trigonal for a pi bond, distorted tetragonal for a sigma bond. And the tetrahedral distortion is crucial for lowering the reorganization energy. The characteristics of the electronic spectrum and other properties depend on the geometry of the bonding. And you can actually classify a large number of kappa proteins by their different bonding type and their different properties. So these proteins are called normal type 1 proteins. The plastithionine is one of them. Another protein called acerine is another one. And they have a pi bond in the blue color. Then by changing ligands, you can change the balance between the sigma and the pi bonding a little bit, and actually you get some rhombic type 1 proteins, nitride, retrobase, and stellocyanine, which has a distorted tetragonal system with a sigma bond or something in between a sigma and a pi bond, and they become green. The color is disappearing for the tetragonal one. It is not going to be blue there. Type 1.5 proteins, some mutants which you can construct. There's even more tetragonal, and the color is now yellow. And finally, type 2 proteins is which you add one ligand. Okay, then it becomes tetragonal, of course. Have a 5-coordinated copper or even a 6-coordinated copper, the color disappears. And you have a standard copper 2. So all these different proteins can be classified according to the binding they make to the cysteine atom. And let me see if I have anything more here. No, I don't think. I think that's my last slide. So this was an example of how quantum chemistry can be used to put light on some structural features, in this case in biochemistry. And of course you can find many of these examples. And as I said before, quantum chemistry is today used a lot in biochemistry to do different things, and it will be used much more. But it is also used in inorganic chemistry to study catalysis, for example. It is used more and more in nanotechnology, and actually the nanotechnology problem is a problem of size, but that problem is more or less solved today. So I think that during the coming 5 years we're going to see an explosion of applications of systems with a few thousand atoms. And then we're talking nanotechnology. I saw a very beautiful calculation by a German called Oxenfeld from Tübingen in East Germany on a conference recently, where he had studied a molecular tweezer, where you have a cage of a rather big molecule and you move another molecule through it. And that was a calculation with about 1,500 atoms. And that is certainly going to be something we're going to do quite routinely in the future. So this area is certainly also going to be an important area of applications of quantum chemistry. We quantum chemists have to learn that we do these things. That is of interest in chemistry. And the chemists have to learn that we quantum chemists sometimes want to do things we like to do, which may not be so terribly useful in quantum chemistry. But there is also molecular physics. One should not forget that. Actually, myself, I'm doing quite some work on diatomic molecules nowadays. That is a word that chemists hate, because that's you quantum chemists, you already do small molecules. We're not interested. But I actually do it because some physicists asked me if I could describe the interaction between two high-spin atoms, keeping their spins high. So not forming any chemical bond, but keeping the spins high. Why did I want to do that? Well, they were doing so-called Bose-Einstein condensation in very strong magnetic field. That was a Nobel Prize in physics a couple of years ago. And they needed these interaction potentials to be able to calculate the parameters to see if this specific pair of atoms would be useful in this context. So there is actually small molecules which are also interesting sometimes. Now these are very heavy atoms on the other hand. So they have their own complexity from that point of view. Okay, I think my time is more or less out, right? Yes, so I think I will stop here. And thank you for your attention.
Questions? You said, I heard you in Boris here today.
Yes?
That when you should use your own geometry when you do your
Yes.
calculation. And that's fine exactly because we can check with a lot of experimental data and we know that our geometries are correct. Can you do this in a liquid phase?
Good question. First of all, if you believe, which can happen of course, that the geometry is different in the liquid phase, it will be a little bit different, but for a stable molecule it will not be much different. And that is not terribly important because you are moving in an energy minimum. A little bit variation down there is not going to hurt you very much. But if you start to think, if you have some very smooth potentials, very weak forces and so on, that the solvent effects become substantial, then of course you have to worry about this. Now, I would say that in most such cases, one would have to look at the case for itself. The general answer is yes, you can do something about it, but you have to be a little bit careful. There are solvent models, electric continuum models, especially one called PCM, and there's another one called Cosmo, which I know PCM is the one we use, and there are other programs have other models, in which you will put your molecule in a cage, and you have a dielectric continuum outside, and then you generate a field from that, and you put that into your calculation. When you do geometry optimization, this is a little bit shaky because you have to have a wall also so that your molecule doesn't go into the cage. But you can also, of course, if you expect that something might depend on specific interactions, which it very often does when it comes to large geometry changes in a solvent, like, for example, hydrogen bonding to water molecules, that you would preferably want to put in as really put the water molecules there, and then you can surround everything again by dielectric equivalent. And then, of course, you can have conformational changes which are quite large in a liquid if you change the dipole moment by changing the conformation from gauche to trans or something, right? That things like that happens, and then you have to be a little bit careful how you treat the solvent. And you can combine, of course, your structure calculations with MD simulations. So you put your molecule in a bath, or water molecule or solvent molecule, and you optimize the structure in that bath and you do MD simulation. Quite computer intensive, but possible. Been done in our group, for example, by studying some esters and some sugars in water by Karlström and his co-workers, where you combine MD and quantum mechanics. You have a force field for your molecule, which you first have to generate, internal, intramolecular force. Yes?
How do you consider relative accuracy of ground state and excited state calculations? Geometry, potential purpose. How far can you go?
Knowledge is limited. The concept of geometry becomes less and more obscure the higher up you get in the excited state. I don't know, those of you who were in Kasambu remember maybe that I showed some pictures of potential curves for excited states, which were all over the place. And they will all be coupled. And if you have a molecule, polyatomic molecule, you have many degrees of freedom in which they can couple. So the concept of geometry is quite difficult if you don't have a state which is very separated from other states. Now, if you have that, which happens, of course, in organic chemistry and such things like that, at least for the lower excited state, then first of all, we have to trust our calculations because there isn't much experiment. We don't know. But I certainly think that, but now I don't think you can use DFT any longer. Accurate calculations using accurate methods, like the one we're using, or in many cases coupled cluster theory, can determine with very good accuracy the geometries of these excited states. Now, as a matter of fact, one of the examples I showed you yesterday was the spectroscopy with the vibrational resolution of two molecules, and we have a number more of these. The relative intensities of the vibrational progressions are extremely sensitive to the changes in geometry. So this is a very good measure of the geometry of the excited state. And if you remember the benzene spectrum, which was top on the experimental one, that makes it conclude that our calculated geometry for the excited state of that molecule is accurate to more than 100 of an angstrom. Better than that. And this is a very easy case because it's still quite bound and the geometry changes are reasonably small. In other cases, this can easily become a mess, in which you cannot even use the Born-Oppenheimer approximation. Yes?
As you word about the future technological advancements we're going to have in, for example, transformation, I would like to listen more specific examples, like what you think about sweet correlated methods, what you think about this related methods. And because I do think technological questions.
Yes.
And also on the open shell, which method
useful. As many questions in one. Yes. I have a friend, I have a couple of friends, as a matter of fact. One of them is Per Sigvard, the biochemist application. That quantum chemistry is dead. It's done. We don't need to do anything more. Now we have to apply it. We have all the methods. They're already developed. And in Per Sigvard's case, it's enough with DFT. This is not true. But it is true to quite some extent, I would say. People continue to develop new methods, and I think for many of these developments that I see around the world, I think are rather futile. They're not going to lead us further. And if they will, finally, all the chemistry is already going to be done by then. Because while we are continuing to develop our methods, these broad freeways of applications are happening all around us. I take, for example, Sigvard's work on enzymatic catalysis. He's gone through maybe 100 proteins by now. When the R12 methods are ready to treat his problems, that's going to be obsolete since long. Nobody's going to be interested to use them. So one has to have a balance here. So what is interesting in chemistry, and we have to have these eyes. I think it's very important for quantum chemists to have to see the chemistry also, and not only their little method that they're so happy about. Also to see the chemistry that they're going to use it for. So they're really applying it there. So there is room for further method development, no question about it. There are problems we have not solved. And I think Dan may talk about some of these more tricky problems when it comes to properties, for example. And there are problems with non-Borin parameter approximations and excited state calculations, which are still quite difficult. There are problems with the environmental effects, which we have not solved. There are problems, and I think the solvent problem, the structure and the solvent and the properties of molecules and chemical reactions in solution, we don't know how to do that today. If you really want to do theory, you have to think, what do we not know now? What is it we need to know? And don't think, how can I improve the last figure in the N2 molecule? That's not interesting. Nobody cares. But if you can do chemical reactions accurately in solution as a function of temperature, then you have done something. So one has to think about, what are the applications you need to concentrate on? What problems are not solved? Chemistry, quantum chemistry is a tool in chemistry, like an instrument in chemistry and in molecular physics, of course. We must think of it as that. It's nothing else today. It's not the fundamentals we have since the 20s. It's actually more technology than theory. Today it's almost entirely technology. So it's important to have that in mind. And then the question, what method to use in a specific context, different people would give different answers to that. Density functional theory works surprisingly well in many cases. When it comes to open shell, I always get a little bit more scared about it because of the near degeneracy that more easily occur in open shell systems between different electronic states. And density functional is sensitive to this. So I don't know. Actually, I don't know. I have a bet with Professor Parinello, which I actually made in 1998. But I will invite him for a dinner in Paris, and he can decide with the restaurant if we are still using density functional theory in 2008. I'm probably going to lose. But but I don't know. It's very difficult. It's a matter of pace, and it depends also on the system. But I mean, people of course choose method after the system. If you're doing the H2 molecule, you don't do it with density functional theory. If you're doing a big protein, you do it only with density functional theory. But one should, when you choose the method, one of course has to be aware of the fact that every method has its limitations and its error bars. So if you go down one step in the methodology, you have to pay for it. But I cannot give you a specific answer of what to use for open shell system. I use MCSF and CAST-PD2 for that. But then, of course, I don't do enzymes. But I will tomorrow, as a matter of fact. Yeah. Okay. Yes?
just running calculation without thinking of attention to the theory or not particular mathematical level of one question. I think why we should pay more attention to the methods they are using.
Well, you can open a journal called Journal of Molecular Structure, TOChem, and similar journals and read through the articles, and you throw half of them away. Because they're exactly that. You run Gaussian, you publish your results. You read the output, and then you write an article. Nothing is more far away from true science than that. Because doing applications in chemistry is extremely difficult and challenging. First of all, you must be a good chemist, so that you know the problem you're dealing with, if you don't deal with trivial problems. I would never have done these calculations on this molecule if I didn't have a new colleague who was a biochemist. I mean, only the fact that he could take out the structure from protein data bank in no time was something I could never have done myself. So it's, you know, you need the chemist, you need a knowledge in chemistry. But you also need knowledge of quantum chemistry. You must be able to choose the method, you must be able to evaluate the errors of the results, etc. You must be able to connect between your calculation and the chemical problem. You have to be able to solve the problem and see all the difficulties. So it is a very challenging, and I find it a pity that it has a lower level of, what should I call it? I lost the word. Sophistication than theory development and the method development. People in quantum chemistry who are doing application are looked upon as a sort of lower class, and those who are doing method development are the real quantum chemists. Nothing could be more wrong than that. I think it should be the reverse. Those who are happy to sit and write a little bit of new programs every day, they're not really doing very much. But those who are applying this in difficult areas of chemistry and trying to see the connection to the real world and trying to use that, those are the real heroes of today's quantum chemistry, in my opinion. But it is not easy. Okay?
Thank you very much.
Thank you.
Thank you.